Okay, so let's do this one from the web work. So did we realize that this is a geometry course? Did we have that realization? And so when we start these problems, we always draw a picture. So what is this? The cap cylindrical surface union of two surfaces. The cylinder given by x squared plus y squared equals 1. And so that's a vertical cylinder with the center axis of the z-axis there. And the hemisphere divide, okay? Z greater than or equal to 1. So we're going to go from 0 to 1 with the cylinder, and then starting at 1, we're going to have the cap, right? Again. Okay, there's a cylinder. And then the cap on top of that. That's not bad. Seems like something's missing. Yes, this is missing here. No, that's the same. Okay. So it's like a really short, squatty silo, right? Like it's a cylinder, and then you've got the cap on the top. And so they want us to find the surface integral of the curl of that thing, right? So here's a big clue. This is curl, right? This is curl. So they want us to do, and then they gave us a little hint there. In any way you like. That's our clue. So, is there another way besides finding the curl and doing the surface integral? That's the question. So we could find the curl of that, which potentially could be ugly. And then we know most surface integrals are ugly. And then we'd have two to do, right? We'd have to do the cylinder lateral surface and the cap. And the sphere is not going to be very friendly because it's moved up 1. So spherical coordinates aren't going to be friendly at all. And neither will rectangular coordinates because we'd be solving for z. We'd have a big long square root, right? So this should be like big light flashing in the sky. Do something else, right? The surface integral of the curl should be very familiar. The surface integral of the curl should be very familiar, especially because the name of this assignment set is Stokes' theorem, right? And that's all about the surface integral of the curl, which is the same as line integral. Okay, so now we got to figure out what line integral is going to be equivalent to this, right? So remember, S for Stokes' theorem is an open surface, which is orientable. It means it has two sides. And separating those two sides is the boundary C. So you have to conceive what I just said for this surface. It's an open surface with two sides, and then what separates the two sides is the boundary C. So if you put an ant on this thing, and it's walking around on one side, say the top there. Okay, here's our ant. Best ant I've drawn all day. And the worst ant I've drawn all day. Because it's the only ant I've drawn all day. Okay, so he's walking around on the outside. So where is the other side? And where is this boundary C, which he would have to cross to get to the other side? So this thing is capped at the top, but it's open on the bottom, right? So the other side, if he's walking around this thing, and you can see him on the silo, the other side is where he's on the inside, like in the ceiling, right? In the ceiling or on the walls of the inside of this thing. And how does he get there? How does he cross over from this side of the surface to the other side of the surface, which would be like the interior walls and ceiling? How does he get there? Yeah.
Cross underneath the bottom circular rim.
Yeah, so this then, right there, is the boundary between the two sides of the surface. So you absolutely have to, there's no way you can do this problem without seeing that. Does that make sense? So this is open down here. And so this is the boundary between the outside. Let's see. That's the boundary between the outside and the inside, right? Or sorry, the one side and the other side, right? It's not really an outside and inside. There's like the top side and the bottom side of this. Okay? So we're going to do if we do the line integral around that of f, it'll be the same as, by Stokes' theorem, it'll be the same as the surface integral of the curl. Okay, so let's do that. So f is, so we're going to parameterize that. So we need r for that surface, r. And what does that mean? It means we have one, if it's a line integral, that means we have one parameter to write all the points on this circle. So what's our one parameter that we're going to use? T, which would represent angle measure, right? Angle measure. And so we know we have r, our x-coordinate is r cosine t, but r is 1, right? So just cosine t, then sine t, and then, okay. So that's our x, y, and z, and then we have this thing f right here. And then we need dr, so dr is negative sine t, cosine t0. And then we're going to use our x, y, and z. Here's our x, y, and z to rewrite f, right? So hopefully we'll get some things to cancel out here. So, yes, because z is 0. 9 sine t. 2 cosine t. Dot that, which comes out to be negative sine squared. And t goes from 0 to 2 pi. Okay, can we do sine squared plus cosine squared equals 1? No, we got different coefficients on there. We don't have 1 sine squared and 1 cosine squared. We have negative 9 sine squared and 2 cosine squared. So just without taking the time to do it, we'll just talk about how do you do the antiderivative of sine squared, remember, and cosine squared. So you'd have to do individual antiderivatives here. Remember the technique for antiderivative of sine squared? Yeah, which one is it? Remember? Yeah, you got it. That's it. That's the half angle identity. For time's sake, we'll just leave it at that. So those aren't bad. It's just it'll be a little bit tedious. But sine squared is what? 1/2, 1 minus sine or cosine? They're both cosine. And this one is minus and this is plus, right? 1/2, 1 minus sine, sorry, cosine 2t 1/2 1 plus cosine 2t. And then you just have a little bit of algebra to do. Okay, does the principle make sense? Right? So this is what? This is using Stokes' theorem. Using Stokes' theorem to find the double integral of the curl by finding the single integral around the boundary. Or in other words, the flux of the curl through the surface is the same as one trip around the boundary of the surface. And we talked about why that was true on Tuesday. Okay, questions on this? So we're actually going to come back to this example and do it a third way today. Do it a third way, yeah.
I was just a little confused because we changed surfaces from a hemisphere to a cylinder, and line integral still works as long as it's open.
So this whole thing together, it's like a piecewise continuous surface. So it's all, you got to see that as all one surface.
Even if it's like a sharp change in the surfaces.
It's actually not, because when you come down to the edge of the sphere, it smoothly connects.
But if it was like differently
Like if it was a triangle cone on top.
I still think it's okay. You just need continuity. You don't need like continuity of derivative. I think as long as, yeah, if you had a cone on the top, yeah, just as long as your surface is continuous, it can have like like a fold in it, like a crease or something. Yeah, Mark.
If you took the cap off and
Uh-huh.
just had an open cylinder,
Yep.
would it just have to be C traversed so that, like, could you cut vertically up and down and then go around the rim also?
No, so now your C would have two pieces. So we need to do two of these.
Would you go around the bottom?
Yep.
Go around the top rim and then cut?
No, you don't cut. You just add them. You don't have to cut. You just go around the top and go around the bottom, and then add them together. So where did we see something like that? We saw something like that before, like with Green's theorem, right? So you can make the cut, but then it cancels each other out, right? You go around and all through it, but then your cut would cancel each other out. So you just end up adding the two. But then you got to get the orientation right, because up on this one, it's going to be this counterclockwise here. But then on this one, you have to go around this way. Remember that? So when you're walking on that thing, you have to have yeah. So right, if the sphere is gone, you can still do it this way, but your line integral is the sum of the two. Other questions? Okay, like I said, we're going to come back to this one. I think we're going to try to do it a third way. Even do it a third way today. Okay, last topic of the course. We made it. All right, we want to talk about flux density. Last time we talked about circulation density. Today we want to talk about flux density. Flux density. So flux density is the rate of change of flow of a vector field out from any given point in the field. So it's the rate of change of flow out from a given point. So circulation density was like what? Like the strength of rotation around a point. So flux density is kind of like it's the rate of change of flow out from a given point. So don't sacrifice listening and understanding for copying, okay? Make sure your note-taking is brain on, okay? Brain on note-taking. All right, so the flux density of point P, similar to circulation density, is you put a small closed surface around your point, and so you're going to have the flux through that surface divided by the volume inside. And so that's why it's a density, because you're dividing by volume. The smaller that volume is, your density is going to go up, right? For the same amount of flux, a smaller volume gives you a higher density. All right, so so what is the flux due to small closed surface? If it's S, then it's going to be, and maybe I should have called those all delta S's. So if you want to change all those S's to delta S's, but you can leave it this way, it's fine. Just as long as you know S is small around P, just leave it that way. Just know that S is small enclosure around P. Then it'd be the limit as the volume gets real small of the surface integral. So that's flux density. All right, so here's kind of a defining example. It's kind of maybe the simplest example, and helps us define this thing, flux density. If you have the vector field x, y, z, and we're going to talk about the origin, and then we'll make our small closed surface just a sphere around the origin, radius a. So let's just look at one point on that sphere. So this point right here. And that's the point xyz. And so what vector do you get at the point xyz according to this vector field? You get the vector xyz, right? So that's what this vector field says. At the location xyz, you have the vector xyz. And so that's just going to be the same length and point in the same direction as what we did to get there, right? So to get to xyz, we actually, that little radius is also the vector xyz because it's positioned at the origin. So this is A. So what's the magnitude then of xyz? Yeah, what is it? And what will that turn out to be? It's A, right? Do you see that the magnitude of that vector is just A? And so then you imagine all the vectors of this field it's constant, right? So on this whole spherical surface, you have vectors of magnitude A pointing out from the center, from the origin, or pointing out orthogonal to the sphere. Does that make sense? That the magnitude of that vector is the same as the radius of the sphere. Okay, so we want to find the flux. And because we have a constant on the surface of the sphere, that vector field is constant. All those vectors have magnitude A. We don't have to do a double integral. Remember, we just said it was the magnitude of the constant vector times the area, and then adjusted for offset from normal, right? That's the cosine theta. Remember, it was F dot S was our formula for flux. And so that was what? That was taking the force in as much as it was in the direction orthogonal to the surface, right? That's what the dot product does. Okay, so what is the magnitude of F for all vectors on the sphere? A. What is S? What about the surface? The area of the surface. And what is theta? So what's our 0? Because all those F vectors are already orthogonal to the surface. So the theta is just 0. So we just end up multiplying A is the constant F for every point on the sphere times the surface area for pi a squared. Theta equals 0 gives us a flux of 4 pi a cubed. So then what's flux density? So flux density will be that total flux divided by volume, which is volume of a sphere, right? as that volume gets small. So we got 4 pi a cubed over the volume of the sphere, 4/3 pi a cubed, which is just 3. So 3 doesn't care what the volume does. The volume can be any size and just is 3. And so we get 3 for the flux density through that sphere, even as it gets small. Okay? So this idea of flux density should also feel familiar. What is flux density like? You said kind of like divergence, maybe? Right? Was it divergence about like expansion and contraction strength, right? All right, so let's take the divergence at the origin. Find the divergence of this vector field at the origin. Remember how to calculate divergence? The curl was the cross product, and divergence was the dot product with what are like gradient, operator, partials. What do you get? You do it. You get 3, right? You take the partial with respect to x, and the partial with respect to y, and the partial with respect to z, and you do what? Add them up, right? The divergence is just the partial with respect to x of the x component, partial with respect to y of the y component, partial with respect to z of the z component, and we add them up. So this isn't really right. This is this operator thing. It's not really actual components. So this is partial with respect to x, partial y, partial z. So when you do the dot product of these two, the dot of the operator with f, partial with respect to x, partial with respect to y, partial with respect to z are all 1. Add them up, 3. Okay, so indeed, flux density is divergence. But this is no means a proof, right? This is just showing one, that's kind of the defining example that shows, it's evidence of it, strong evidence that flux density is divergence. Okay, questions on that? So we're going to kind of look at something of a proof here next. So questions on anything on the screen? Can I go on? Okay, so let's look at something of a proof here. So we have a solid E with a boundary S. So imagine this comes some kind of thing formed by surfaces, right? But it's closed. So the boundary is make sure it's closed. Okay. So just the boundary of E is going to be now a closed surface, right? Rather than having one side and another side, it has an inside and an outside, okay, for a closed surface. And we're in the vector field F. Okay, so we're thinking about now chopping this up into 3-dimensional little elements, and we'll call each one a box, right? So you can kind of see how this thing is chopped up. And you imagine it's made up of a bunch of boxes, okay? So here's one box. Here's one little tiny box. It has a volume of delta x, delta y, delta z. And at that box, there's some vector of the vector field, PQR. And we'll say it's at x naught, y naught, z naught. So we've got the one little tiny element of our solid, and then we have the vector of the vector field associated with that solid. Okay, and let's look at now the p component of that vector. And in fact, the change in the p component from the front to the back. So in front here, it's kind of the change from the back to the front. So what changes? The x component changes by the amount delta x from here to here. And so I have the p component kind of back there, and then the p component up here, and they're different in their x by the change in x. All right, so the flux density then is going to be what? We're going to sum up in all three dimensions the flux density, the flux density for each of three dimensions, right? It's going to be the flux density due to the x, flux density due to y, and flux density due to z. We're going to add those three up. And so we know that's going to be the flux divided by the volume. It's going to be the total flux through the small cube over the volume of the cube. That's just the exact same thing we said on the previous slide about what flux density is, but instead of the sphere in our example, now it's going to be a little cube. And so to get the flux to the small cube, like I said, we're going to add up the three components, three different directions. Okay, so I'm just kind of focus on the direction I'm showing, the x direction. So the flux is going to be the change in P times the area, right? So what do we say? Flux is F times A. So what in the x direction, what would the area be? The area would be delta y times delta z, right? So it would be the P component, so the x component of F times area. And we'll do the same thing for the other two directions. So right now I'll just focus on the one. The other two are exactly the same. Change in Q times delta x delta z, change in R times delta x delta y. And that whole thing over the volume of the cube, which you know is delta x delta y delta z. So then what happens if we split this up into three fractions? Do you see what happens here? I have delta y delta z and then over delta x delta y delta z. So we're just going to have over delta x. So it's like the change in P over the change in x. And this will be the change in Q over change in y. And this will be the change in R over change in z. And as things get small, that's our partial derivatives. So we can say this is as delta v goes to 0. And that's divergence, right? That's divergence. So that's kind of a conceptual outline of the proof. So this flux density, this is showing that the flux density at x naught, y naught, z naught is the same as the divergence of F at x naught, y naught, z naught. So then the flux, here's another way to compute flux. So the flux out of one box would be the flux density times the volume, right? Because the flux density is flux per volume, right? It's a rate of flux. Then the flux would be that rate times change in volume, right? So remember the old idea, it's back again, right? dy equals dx. The divergence is expansion rate of change times a little change in independent, which is our little change in volume, gives us what? A little accumulation of flux. Little accumulation of flux is the rate of flux times little change in independent, which in this case is a three-dimensional change, a dV. Okay, questions on this slide? You're still tuned in, right? Okay, so this is, then we've got all the pieces for the divergence theorem. We want to sum up all the flux out of those boxes across E. And just like we've seen before, there are two ways to do this. The first way is what we just looked at on the last screen. Sum up all the rate times little changes of V. So sum up the flux for every box using the rate of change of F, the rate times a little change in V, and then sum all those up. And that'll be the total flux for E. The other way is to think about summing up little surface integrals of F for all the boxes. So here's a box. Here's the box next to it. Here's the box below it. Spread them out a little bit. So these are all packed in there, packed into E. And we're going to do the surface integral of F for all those boxes. So, and assume outward orientation for all those boxes. So what's going to happen? We've seen this before. What's going to cancel? All the pieces that are touching. When we do the surface integral around all those boxes, all the pieces that are touching are going to have an equal and opposite canceling effect. And what's going to be left? Just the outside. And so it'll be, this will be equivalent to. So summing up all the surface integrals of F for the boxes will be equivalent to. It's not a line. So what is the boundary? It's not a line anymore. What's the boundary? Surface. So we'll get to the outside and we'll be summing up all the surface integrals of. So when we get to the outside where they don't cancel, it's going to be all these edge pieces, right? The surface integral on all the edge pieces will be left, and that will be the surface integral of the whole boundary of E, which will be that. So when we sum up all the divergence times the little changes in volume, we sum all those up. As things get small, that's like the triple integral of the divergence of F dV. Okay, summing up all the flux for all the little boxes as calculated by rate of change times change in independent, right? M dx. Or like that, right? But because it's dV, it's a triple integral, right? We're going to do a triple integral to add up all those boxes. So the divergence theorem. So we've got it. Divergence theorem. So these are both two different ways of calculating the sum of all the flux out of all the boxes. Either do it all by the rate of change times sum them all up by rate of change times delta V, or just do the surface integral of F around the outside. So if E is a solid with a piecewise smooth boundary S, and if F is a smooth vector field everywhere in E on S, then those two are equal because they're both the total flux across E. So look. What do we got? We have the accumulation of flux, of little bits of flux, right? Each calculated by rate times change in independent. And what's that equivalent to? Total change around the boundary. Have you heard that before? So, accumulation of lots of little pieces, each calculated by rate times change in independent, is equal to, it's another fundamental theorem, right? So this is rate of change. This is accumulation of bits, in this case bits of flux. Can be also described as, or can also be calculated as, the net change, the total change at the boundary. The total change at the boundary. This is another fundamental theorem. We're up to 4 now. 4 in this course, right? They all have the same parallel structure and idea as the original fundamental theorem in Calc 1. So what would it mean to verify the divergence theorem? Do both, show that they're equal. What would it mean to use the divergence theorem to find a surface integral of a closed surface? We want to use the divergence theorem to find the surface integral of a closed surface. What would it mean if we're using the divergence theorem to do that? You would calculate a triple integral, right? You calculate a triple integral of the divergence of f. Okay. So I want to go back to a week ago, a week and a half ago, like last Tuesday before Thanksgiving, we just talked about flux integrals, and then we got to do 2 in recitation, which I put on the video. So I want to talk about those. Any questions about divergence theorem before we? So we made a mistake in both of those. So let's do this one first. So we started this in lecture a week ago Tuesday, and we finished it in recitation, and we wanted to find the flux through S, which is the closed surface. I should have said that is the boundary of, the part of the unit cube below y plus z equals 1. It was this like wedge, right? So the surface was this closed surface that had 5 pieces, right? 5 different planar sides. And we want to find the surface integral. Okay, and so that, I think that answers the questions about having edges, right? Remember you were asking about the edges? Yeah, so it's totally fine, right? Because this, like we did the total surface integral of this is just add up the sides. So it just has to be continuous. There can't be any gaps or tears in it. As long as it's totally closed and continuous, you can have kind of sharp edges. All right, so what was the problem? So the problem was what we said about our flux integral. So we had 2 formulas for doing this. We said one was f dot ds, which was f dot what? Ru cross RV du dv. So that one's fine. This is cross. But then we had this other one that kind of where that came from. Where that came from was s f dot n ds. And so what we said was, or what I said, you went along with me, that's fine because I said it, was that as long as you have a planar surface, use the second form because n will just be constant, and just find that unit n, and then do f dot n and then ds, which is fine, except ds is not the same as du dv. ds is not equal to dA. And that was our mistake. ds equals so what does ds equal? ds equals the magnitude of RU cross RV dA. So we were forgetting this. I was forgetting this part here. So I was just, when we were doing this way of doing this dot n, then we would just put du dv here, whatever it was, dx dy or dr d theta, whatever we chose for our u and our v. When really ds is the magnitude of the cross product dA. So this would be right if this were 1. And this is 1, this equals 1 when you have a rectangular region parallel to a coordinate plane. It's fine, because then it equals 1 and your ds does equal dA. But if you have a slanted plane, or you have a non-rectangular plane, like non-rectangular region, like a circle, then you got to do this, or you've got to also find the magnitude of RU cross RV. So does that make sense? You can only assume that this is 1 and ds equals dA if you have a rectangular region parallel or in one of the coordinate planes. So for this example, we assumed, so for the bottom, it's fine, right? It's a rectangular region parallel to the xy plane. The left side, perfectly fine. The back side, perfectly fine. Front side, for all those sides, it was fine that we just said ds equals dA because that magnitude of the cross product was 1. But where it was not okay was for this angled plane. For this angled plane, we found that this vector was 0, radical 2 over 2. I'll do it in red. We said this was 0, radical 2 over 2, radical 2 over 2. And then we just did, so right here you can see, I just did it. I just did f dot that n vector, which I just wrote in red here, and then I just did dx dy. And that's not right. Because we also need this RU, this magnitude of RU cross RV in here. Okay, are you following me? So it's going to change this answer. So the only two that had a positive flux were the angled plane, and which one was this? 0 to 1 minus z, 0 to 1, y. Is that the front? Is that the front? Okay, so the front we were fine, but this angle plane is going to be different. And so the magnitude of, what is the magnitude of RU cross RV? If you do the math, you get radical 2. So we need another radical 2 multiplied in here. And that's this RU cross RV for that diagonal plane. So what's the moral of the story? Just always, since you have to do the magnitude of the cross product, just always use this. Unless, so always use this form for surface integral, unless you have a rectangular or like triangular region parallel to a coordinate plane, then you're okay to say that that thing is 1 and ds equals dA. Otherwise, you have to do the cross product anyway, so might as well just use this form. Okay. Does that make sense? Okay, some nods. Good. So now what was this then? What should this been? So since it's just a factor of radical 2, then we can just multiply the answer by radical 2, right? It's just a constant. And so what do we get? 5 times 2 is 10 over 12. 5/6, right? 10 over 12 is 5/6. 5/6 plus 1/6 equals 1. So the answer to this should have been 1. Not this weird thing with a square root. Okay, any questions? Make sure you know that because that's going to be really important for surface integrals. So when in doubt, you can just use this form always. It will always work. And don't use this form unless you're confident you know what you're doing. I mean, so what you can do is you can always use it when you have a rectangular or like triangular or trapezoidal region, something like that, just not circular, parallel to a coordinate plane. Then you can assume that thing is 1, and those things are equal. So that's why it works for this, for the front. Okay, so now we do the same problem. I want you to do it a different way. Find the flux through S, the closed surface that's part of the unit cube below y plus e equals 1. I want you to find that flux a different way. And when you find that flux a different way, you should get the answer of 1. Go.
Surface integral like curl.ds? Because I had a similar case where I was looking at a plane and it had like the normal coming out, but it didn't want to kind of like change it.
Well, yeah, so it's
The
still a
same thing.
surface integral.
Yeah,
So your f is a different f.
Yeah.
Scroll of f.
Yeah.
Same thing.
Same
Yeah.
thing.
Yep. I'm going to try to get some homework back to you. Adam, John, Ian, William. I'll do this. No name. George. Adrian. William. Laura. Okay, so this is perfect setup for the divergence theorem, right? So the double integral, do it in blue. What happened? It all went away. Double integral of f dot ds s is equal to? We have all the conditions for the divergence theorem. So it's the triple integral over e of divergence of f dv. And this is a pretty, once you do that divergence of f, this is a pretty easy triple integral over that solid. Okay, so that's getting, if you never got started, that's how you get started. And then then it's just a triple integral. Divergence of f is just a scalar function, and you're just doing a triple integral. You could do top to bottom first. You could do dz, and then projection into xy plane, dy dx. And you get 1. I'm not going to write the whole thing out, but you get 1. Okay, so we made the same mistake on the other example in recitation. So let's correct that too. So the other example we did in recitation was the cone. This one. And so the actual cone part, S1, so this was the flux through the closed surface, that was the cone and the top disk. Okay? So we actually the cone we took the cross product, we did it by the cross product, so that's fine. Okay, but then when we did the top disk, the S2 part, we made that same mistake. We just said n was 0, 0, 1. So right here, here's our n vector, which is pointing up like this, which is correct. But then we left out, if we're going to do this form of it, f dot n, it's ds, not dA. And so ds has in there, it has the magnitude of r cross r theta. Okay, and this is our r. So this was our r for that top disk, x, y, and z equals 4. So then if we're going to use this f dot n form, we also need the magnitude of r cross r theta, which is not 1. Okay, if you do that cross product and take the magnitude of it, you get r. R meaning the radius. So we got two r's right here, right? We got the r standing for the parameterization of the region, and r meaning this r. So you make sure you get your r straight. So this is r. So we need another r in there. So you don't get 2 pi over 0, 4 to 0, 4 dr d theta. You end up getting 4r dr d theta. And had we just gone ahead and used the other form, the f dot cross product form, we would have gotten this, 4r dr d theta. And the reason it doesn't work is because this is circular. It's not like rectangular, right? It's not rectangular or triangular. So I blew that too. The same mistake. All right. So when you sum those up, do I have my notes or not my notes? When you sum those up, you get 64 pi. This turns out to be, this here is 64 pi, blue and blue. So this is 64 pi. And this is negative 128 pi over 3. And so the total surface area is 64 pi minus 128 pi over 3, whatever that is. Not surface area, total flux, right? Total flux then, f dot ds is 64 pi minus 128 pi over 3. I want you to confirm that answer another way. Confirm that answer another way. Go. Okay, so just what will it be? What will be the alternative way to do this? We have a closed surface. We need the flux through a closed surface. We can also do that as triple integral of the solid that it encloses, right? Of the divergence. What coordinate system are you going to use for this one? Yeah, cylindrical, which is polar in 3D. That's right, cylindrical. So we're going to use cylindrical coordinates, which is dv is r. So this is now. So when you say dv, This is now changing from, like, say, rectangular into. So dv is always r dz dr d theta. So don't forget the r. Okay, z goes from, so the divergence of f is, what's the divergence of f? 1, right? It's just 1. And so what is this then the surface integral equivalent to? If we're doing the triple integral of 1 dv, what are we really finding? We're finding volume, right? When your integrand is 1 dv, this will be volume. So that would be nice if we had the volume of a cone at our right cone at our fingertips, but we don't, so we can go ahead and evaluate the integral. So either way, so z goes from what to what? Good. So this is this cone is z equals square root of x squared plus y squared. So what is the square root of x? So z is going to go from the bottom is the cone, the top is the horizontal plane. So z goes from square root of x squared plus y squared, which is r. So the bottom of this is r up to 4. And then we're going to do dr d theta, which is the projection of this thing into the xy plane, which is r goes from 0 to 4, theta, 0 to 2 pi. Got to remember everything we've done. And if you do that, you should get the same thing, whatever. 64 pi minus 128 pi over 3. You do. And if you take the volume of a cone with radius 4 and height 4, you should also get that same thing. So we'd have to look up the volume. I think it's 1/3. 1/3 pi r squared h. And does that turn out to be the same thing? It should. Just because that integrand turned out to be 1. Okay, I want to get back to that Wilbur problem. Talk about that Wilbur problem. Please ask if I lost you, because there's probably other students who got lost too. So don't hesitate. Anybody have a question? Who's thinking, I'm just going to walk up and ask them after class? Okay, please, thank you. You're talking about this r dz dr d theta? This thing? So there were two ways that we talked about doing the surface integral. F dot RU cross RV dA, and then we had where that came from was F dot N ds. Okay, so when we did the problem originally, I made the assumption that ds was the same as dA, when it's not. ds is the magnitude of the cross product dA. So whenever I was doing this, if we didn't have a plane that was perpendicular to one of the axis plane, this thing is not 1. So this is not necessarily 1, meaning that ds is not just equal dA. But when we were using this before, I was always saying that ds was dA. So this top circular disk was one example where this thing does not equal 1, it actually equals r. So I had to include that r in the integral. That was a mistake that I made when we did it in recitation. So bottom line is you can always use this. It will always work. if you want to use this, then make sure you know when you can without finding the cross product and just assuming ds is dA. Does that solve it? Does that answer it? Okay. Other questions? Would you do me a favor and shut that door? All right, other questions? All right, I want to talk, thanks. I want to talk about that web work problem. Go back to that web work problem. So we have this integral, we're calling the surface M, of what? Curl of F dot ds for this thing, right? So, is this a candidate for the divergence theorem? So does this, for this particular M, does it equal the triple integral of the divergence of that? Why not? It's not a closed surface. But what would it be? So if we did that, so if I did the divergence of the curl, if I did the divergence of the curl of F, right? Because now this thing is curl, right? Could we use that to help us? So they're not equal, right? They're not equal because this is not a closed surface and it's got that open bottom. So these are not equal. But could I use the divergence theorem to help us get that surface integral? What would I do? Andrew? Subtract the flux out of the bottom, right? Because the flux of M, flux through M, plus the flux through the bottom disk would then equal the divergence because that would be a closed surface. So if I want, I can calculate this by subtracting the flux of the curl FDS out of the bottom disk. And because z equals 0 and it's a nice easy disk, this might be easy to do. And the solid may be easy as well. But now notice, this vector field is the curl of another vector field, and so I need the divergence of that, right? It's the divergence of whatever that is. So I was hoping we'd have time to crank that out and see if we got the right answer, but we don't. So, but that's the roadmap for that. Okay, I have one more homework to get back to you. Let's see.